Hello everybody, this is BTech 9008 Bioprocessing Seminar and you are watching the manufacture of gentamicin. First, let's do some introduction. Gentamicin is a broad-spectrum aminoglycoside that has rapid bactericidal effect against most gram-negative and some gram-positive bacteria. Its structure can be seen in Figure 1. Gentamicin is produced fermentatively from rare actinobacteria species Micromonospora purpurea. Gentamicin can rapidly inhibit or induce error in protein synthesis by binding irreversibly to the A site of 13S ribosomal subunit. However, abundant available energy is necessary for the uptake of gentamicin. Because of that, it is ineffective against most anaerobic bacteria. Its mechanism can be seen in Figure 2. Gentamicin was discovered in 1962 by Marvin Weinstein teams while studying soil samples provided by a medical virus. It was first patented in the same year in US to Weinstein Company and was approved for medical use in 1964. It is remained in wide use until now. Next, let's go through the manufacture process. The first thing we need are raw materials, and one of them is an industrial strain of Micromonospora purpurea. The earliest industrial strain was found by Weinstein himself, and it was wild-type bacteria. However, newer industrial strains are often genetically engineered to increase gentamicin yield. Another raw material is fermentation broth, which compositions greatly affect gentamicin yield. It typically contains a carbohydrate source, a protein source, calcium ions, and trace elements. The process begins with starting the culture. A lyophilized bacterial sample was checked on nutrient agar plate. After 4 to 6 days, pure colonies from agar plates was transferred onto shake flask containing fermentation broth. After 3 to 4 days of inoculation, culture broth from shake flask was transferred onto agitated seed tanks. After that, the bulk fermentation process begins. After 3 to 4 days, culture broth from seed tanks was transferred into fermentation bioreactors, with capacity up to 200,000 liters. Various factors are constantly monitored and controlled optimally for the bacteria. Image and structure of agitated bioreactors can be seen in Figure 6. Tanks are constantly air-pumped and agitated, and because of that, anti-foaming agents are added to prevent bubbling. In these tanks, bacteria proliferate and produce gentamicin as secondary metabolite. After 3 to 5 days, maximum amount of gentamicin was produced, with up to 880 mg per liter, and the extraction and purification process begins. Gentamicin is typically extracted and purified with a 5-step process as follows. First, fermentation broth was filtered to remove insoluble particles, typically by a rotary vacuum filter drum, which structure showed on Figure 7. The drum surface was pre-coated with filter aids to increase filter performance. Common filter aids include perlite or diatomaceous earth. After that, gentamicin was captured by passing the filtered broth through a column packed with weak carton exchange resin, which mechanism showed on Figure 9. Gentamicin, being positively charged, was absorbed to the resin due to its high affinity. Then, a strong inorganic acid was passed through the column to elute gentamicin. Eluate contains gentamicin was collected for the next step, which is decolorization. The eluate was passed through a column packed with strong anion exchange resins to absorb impurities. Mechanisms of anion exchange was shown on Figure 10. Activated carbon might be added to the secondary eluate for an additional bleaching. This tertiary eluate would then be filtered again to obtain final crude gentamicin solution. The next step would be crystallization. Originally, gentamicin solution was concentrated in vacuum, but modern methods involve free drying to obtain high purity gentamicin powder. Industrial scale free dryer can be seen in Figure 12. The purity of gentamicin powdered after this step can be 18% or more. Gentamicin powder can be further purified by solvent precipitation or high-performance liquid chromatography to achieve designed purity. And the last step would be refining, where gentamicin would be processed into various forms such as eye drop, pill, ointment, chemicals, etc., which picture showed on Figure 15. The final product would be ready for packaging. Now, let's take a look at the quality control process. Quality control is of utmost importance in the manufacture of gentamicin. Manufacturers of gentamicin active pharmaceutical ingredients or API should provide evidence for GMP compliance and API quality documentation according to World Health Organization guidelines. The entire manufacturing process was quality controlled, from lyophilized bacterial sample to post-packaging process, as shown on Figure 16. Many factors regarding strain, equipment, fermentation broth, or other parameters must be satisfied before moving to a next step. Especially in the United States, antibiotic production like gentamicin is put under strict regulation by the FDA. Each production batch may be subject to more testing to have FDA certification. Only after that, the batch can be sold for general consumption. Finally, we have to take a look at the future of antibiotics. Antibiotic resistance has become a global crisis, resulting from misuse of antibiotics like gentamicin. Figure 17 here showed worldwide resistance of Acinetobacter baumannii to aminoglycosides. Besides searching for novel antimicrobial compounds, regulation on the use of antibiotics is crucial to slow down the resistance process. These are the references that were used in this presentation. And the bioprocessing seminar about manufacture of gentamicin has come to an end. Thank you for paying attention.